In this video, I want to talk about the mesh current method. So before I begin, let's just quickly go over this circuit. So we have an independent voltage source. We have 8 resistors that are connected to this voltage source. So overall, if we are thinking of going with the initial approach that we did for our circuits, for each one of these resistors, we need to have both their voltage and their current to be figured out. And also for this independent voltage source, we need to find the current. So since we have 8 resistors, that translates to 16 unknowns. We have one voltage source too, which translates to one unknown, which is the current of the voltage source. So in total, we need to have 17 simultaneous equations. But then we said, okay, we don't need to find 2 variables or 2 unknowns for each one of the resistors, because if we know the current, we can easily use the Ohm's law to get the voltage. Or if we know the voltage, again, we can easily use the Ohm's law to get the current. So that was reduced to 8. For this one, we still need to find the current. So for the first simplification that we could make, we could solve 9 simultaneous linear equations to be able to fully solve this circuit. We could have some other simplifications as well. The other simplification was, are there any elements that are connected in series? If that's the case, that helps us reduce the number of equations too. For example, we have R1, Vs, and R5 to be in series, right? So if we know one current for them, that's basically the current for the other two as well. So 2 equations will be reduced easily here. So that brings the total number of equations that we need to solve to 7. Another simplification was whether we have 2 elements that are completely in parallel. In that case, we could have reduced the number of equations even further too. But as you can see here, we don't have such a case. So based on going with the systematic approach, we still need to find 7 simultaneous equations, right? Which is a lot for a circuit like this. So in the previous videos, we talked about the node voltage method. So we said for the node voltage method, first we find all the nodes in our circuit. So we have a node here, another node here, then this one, this one, this one, and this one. So overall, we have 6 nodes. So we said what we can do is to consider the node with highest number of branches connected to it to be considered as the reference, right? And then we basically went only through the essential nodes, not necessarily all the nodes. So how many essential nodes do we have here? This one is not an essential node. This one is also not an essential node. But these 3 are essential nodes, right? So we could write solve this circuit using only 3 node voltage equations. So there is another way to think about this circuit too, and that is the topic of this video, which is the mesh current method. So for the mesh current method, we use the current that go through the individual meshes. So do you remember what was the definition of a mesh? So a mesh was a loop or a closed path with no other loop inside of it. So that was the important condition. So a loop was any closed path in the circuit. As long as we didn't go through elements more than once, it was considered a loop. So for example, this path, Vs, R1, R2, R3, R4, and R5, that creates a loop. But that loop is not a mesh because it contains this loop, and this loop inside of it. So a mesh is a loop that doesn't have any other loops inside of it. So mesh current method is only applicable to planar circuit. You remember what we meant by planar circuit, so I don't repeat that. So now let's just see how we can use the mesh current method. So in order to use mesh current method, we need to define new variables, which are the currents that go through each one of these meshes individually. So here we have 4 meshes in this circuit. So let me just clear these nodes so they are not confusing to us. So we have 4 meshes here in this circuit. For each one of them, I define a current. So we have current I1 going through this mesh, current I2 going through this, I3 going through this one, and current I4 goes through the last mesh. So one thing that might cause a question is that let's say for the first mesh, we have I1 going through R1, R5, and Vs, right? Because for these one, there is no other current that you can say can go through them. But what about this R6? Because it is common between the first mesh and the second mesh. What is the current for this resistor? The same is true for R8 too. What is the current that goes through R8? Is it I2? Is it I3? Or it is a combination of them? What about R3? Right? R3 is also common between R4 and R3. Between I3 and I4. What about R2? R2 is common between I2 and I4, right? So we will get to the answer of this question later. So mesh current method requires this number of equations for any circuit. We have BE, which is the total number of essential branches. So BE is the number of essential branches. Do you remember what was an essential branch? An essential branch was a path that connected two essential nodes. So for example, this branch is an essential branch, R1, Vs, and R5, because it connects these two essential nodes. So how many essential branches do we have here? So if I highlight the essential nodes in this circuit, we have one essential branch here, the second one is R2, the third one is R6, the fourth one is R8, the fifth one is R5, the sixth one is R3, and finally the seventh one is R7. So in total we have 7 essential branches in this circuit. The next variable is NE, which is the number of essential nodes. So how many essential nodes do we have here? We have 4 essential nodes. So based on this, we have 7 minus 4 minus 1, or 4 equations that we need to write based on the mesh current method to get to the solution of this circuit. So now that we have this, let's just see what is the formal definition of a mesh current. A mesh current is the current that exists only on the perimeter of a mesh. So for example, we have this mesh 1 here. I say, okay, we have current I1 for this specific mesh. This is mesh 2. I say I have current I2 for this specific mesh. Mesh 3, I have current I3 for this specific mesh. And finally we have mesh 4, which I say I have current I4 for this specific mesh. So let's just repeat the definition again. A mesh current is the current that exists only on the perimeter of a mesh. So there is a fine distinction that we have made here. We don't say a mesh current is the current for all of the elements of that exist in the mesh, but rather it is a current that you can say fictitiously exists for that specific mesh. So because of that, the mesh currents are not necessarily branch currents. So for example, for mesh 1, I1 is branch current for R1, R5, and Vs. Why? Because they only belong to mesh 1 and they are not shared between two meshes. But for R6, I1 is not the branch current. In fact, since R6 is shared between mesh 1 and mesh 2, the branch current is a combination of I1 and I2. We will get to that later. But just keep that in mind, that for any element that is not common between between two meshes, for that specific element, the mesh current is equal to its branch current. But for the component or for the branches that are common between several meshes, in that case, the mesh currents are not equivalent to the branch current. There are some cases that the mesh current cannot be even measured using an ampermeter. So if you want to measure I1, you can easily put an ampermeter here in series with these components and find I1. But what about I2? As you can see, these three components create the second mesh. But all of them are shared between two meshes. So R2 is shared between mesh 2 and mesh 4. R8 is shared between mesh 3 and mesh 2. And R6 is shared between mesh 1 and mesh 2. So if I put, let's say, an ampermeter here in series with R2, what I'm measuring is actually the combination of I2 and I4. Whatever that combination is created, which I will get to it later. The same is true if I put the ampermeter here, or if I put it here, right? So none of them would give us actually the mesh current I2. So the conclusion is that mesh currents are fictitious, right? But they are very useful. So now that we saw this, let's just go over a very basic example. And I will get to that circuit in the previous slide later. So for this basic circuit, we have two independent voltage sources, V1 and V2, and three resistors. Just by looking at this circuit, you can easily see that if we use the node voltage method, we can write down the equation and the solution only using one equation, right? We have two essential nodes. If I consider this to be the reference node, and let's just say I call this node 1 and I assign V1 here. What I can write is just simply write the KCL for all the current for all the exiting currents from node 1 like this. So we have let me just call this Vn and I call this node n, so there is no confusion. So we have Vn minus V1 over R1 plus Vn over plus Vn over R3 plus Vn minus V2 over R2 equals 0. And if I know V1, V2 and all the resistors, that means that I can easily find Vn, right? But for the purpose of this video, I want to explain how the mesh current is derived. So I assume that we don't want to use the node voltage method. So let me just erase these so you're not confused. So in this circuit, we have 3 essential branches. We have 2 essential nodes, this one and this one, and we have 3 branches that connect these 2 essential nodes together. So we can write 1 equation from KCL and 2 from KVL based on the currents that we defined for the individual elements. So this is still using the systematic approach. We have the KCL for node 1. So that is negative I1 plus I2 plus I3 equals 0. So if I rearrange that, that is what I get. Then we have these 2 loops. So if I start from this point, I have negative V1 plus R1 I1. So following the passive sign convention, I consider the polarity to be like this, plus I3 R3 equals 0, which if I rearrange it, it will be the second equation. And finally for this one, if I again start from this point, since I3 is from top to bottom, but we are going from bottom to top, so in the opposite direction of the voltage drop, I use a negative sign. So we have negative R3 I3 plus, following the passive sign convention, we have R2 I2, and then we have positive V2 equals 0. So if I rearrange this equation, this is what we get for the third equation. So in these 3 equations, if we know V1, V2, and R1 and R2 and R3, we have 3 equations that give us the values for I1 and I2 and I3. We can replace, in order to solve it, we can replace I3 with I1 minus I2 from the first equation. So that is for us to have a 2 by 2 linear system. So we basically eliminated one of the variables, right? But even if we don't do it, we can easily use this system as a 3 by 3 linear system and solve for I1, I2, and I3. So the result of replacing I3 with I1 minus I2 is this. So we have V1 to be equal to I1 multiplied by R1 plus R3 minus I2 multiplied by R3. And negative V2 equals negative I1 R3 plus I2 multiplied by R2 plus R3. So if you look closely, something that can cause questions and may be interesting is that we have R1 plus R3. It looks as if they are in series with each other, right? Because we said if we have resistors in series, we can calculate the equivalent resistance by summing the resistors. The same is true for R2 and R3 here too. We have R2 plus R3 here. So it looks as if R2 and R3 are considered to be in series, right? In fact, more accurately, as you can see here, we have R1 plus R3 considered to be in series, but since we have R3 common between this loop and this loop, and we practically considered it twice, we just have a term that subtracts the contribution of R3. The same is true for this one too. So that is the basic idea behind the mesh current method. So let's just write the equation based on the mesh current method. So based on the mesh current method, we find all the meshes that we have in the circuit, and we assume that each one of these meshes has a current for itself. So considering this, we have two meshes here. I consider this one to be mesh A with its current to be IA, and I consider this one to be mesh B with its current to be IB. So generally speaking, we usually substitute the NE-1 current equations into the BE-N-1 voltage equations. That is something that we did in the previous slide. So the mesh current method is a systematic way of doing such substitution. So now that we have this, let's just write the linear equations based on the currents that we have defined. So let's just go in the direction of this current and see what we can write as the KVL for this mesh. So if I start from this point and go upward, first I need to write negative V1, right? Again, following the passive sign convention, as we always do. When we basically enter an element from the negative side or from the opposite side of the voltage drop, we consider that to have a negative sign. So that is the negative sign here. Then we have R1, which has the current IA going through it, and R1 is not shared with any other mesh. So its voltage according to the Ohm's law and also following the passive sign convention is going to be R1 IA. And then the third element in this mesh is R3, which is common between mesh A and mesh B. So that's where we need to come up with a plan to be able to handle these elements that are common between different meshes. So the way to handle it is very simple. As you can see for R3, we basically have two competing currents. We have IA to be going from top to bottom, and we have IB that is going from bottom to top. Since we are going in the direction of IA for now, and following the passive sign convention, we can say, okay, we are entering from the positive side and exiting from the negative side of the resistor. So if we have IA going from the positive side to the negative side, and we have IB going from the negative side to the positive side, what is the net current that goes through R3 in the direction of IA? The answer to that is very simple. It's going to be IA minus IB. So we have R3 multiplied by IA minus IB. And by doing that, we got to the first point of our mesh. So again, we are going in the direction of IA. For this element R3, which is common between mesh A and mesh B, we have two competing currents. One is IA, the other one is in the opposite direction, IB. So what is the net current that goes through R3 in the direction of IA? It is IA minus IB. So this will be the first equation that we can come up with. So let's just do the same now for the second mesh, mesh B. I start from this point. So since we are going in the direction of IB, following the passive sign convention, we just consider this to be positive, this one to be negative. So we have IB going from bottom to top, and we have IA going from top to bottom. So in the direction of IB, what is the net current that goes through R3? The answer to that is going to be IB minus IA, because they go in opposite directions. So we have R3 multiplied by IB minus IA. Now we get to R2. For R2, since it is not common between two meshes, its current is going to be the IB itself. So we have R2 IB, and finally we go through the positive side of this voltage source. So it's going to be positive V2 equals 0. So this is the second equation that we are writing based on the mesh current method. So to recap, we find all the meshes in our circuit. For each one of them, we define a representative current. So that representative current is only available or is only exists on the perimeter of the mesh. So it's not necessarily a branch current. For some of the elements, it can be a branch current, but that's not necessary. And then we write the KVL based on those currents, those mesh currents. If there are elements that are common between two meshes, we need to find a relationship between the competing currents. So if they are in the opposite direction, we use a negative sign. If they are in the agreeing direction, so if, for example, if IB we defined it in the opposite direction, so for R3 they would go the same way as IA. So if they are in agreeing directions, in the same direction, we add them together. If they are in the opposite direction, we subtract it. And then based on that, we write the KVL for each one of those individual meshes. So we apply KVL around the two meshes, expressing all voltages across resistors in terms of mesh currents. And these are the two equations that we come up with by applying the mesh current method. So now let's just take a look at the two sets of equations that we have found. The first one was by using the systematic approach. The second one is by using the mesh current method. So if you look closely, you see that based on these two, this one I wrote it wrong. This one is based on the mesh current. This one is the systematic approach. This one is the mesh current. So if you look closely, you see that IA and I1 are exactly the same. IA equals I1. Also, we see that IB and I2 are exactly the same. So that means that trying to solve the circuit using the mesh current method is basically the same result as the systematic approach, but with less steps for calculating the equation. Of course, here we have a very basic circuit. If we have more and more complex circuits, then the reduction in the number of equations that we need to write is going to be even less. So these are the conclusions that we had based on comparing these two techniques. So now that we saw that very basic example, let's just try to write the mesh current equations for the more complex circuit that we saw at the beginning. So we have mesh 1 here, mesh 2 here, mesh 3 here, and mesh 4 here. So what we did was that for each one of these meshes, we defined the current. And now we want to write the mesh current equation, basically the KVL based on the mesh current equation. So let me just start from this point here. So following the passive sign convention, we have negative Vs plus R1 multiplied by I1 plus R6 multiplied by I1 minus I2. So as you can see here, R6 is common between the first mesh and the second mesh. And based on the directions that we have specified here, they are in opposite directions. So I1 is going from top to bottom, I2 is going from bottom to top. So that's why we have this with a negative sign, with a subtraction. And then finally we have R5 multiplied by I1, which equals 0. Let's just write the equation for the KVL for mesh 2. So for mesh 2, I start from here. So we have R6, which is common between mesh 1 and mesh 2. Since we are going in the direction of I2, the net current in that direction is going to be I2 minus I1. So I use I2 minus I1. Then we get to R2. We are going from left to right in the direction of I2, but we have the competing current I4 going from right to left. So we have R2 multiplied by I2 minus I4 And now we get to R8. So for R8, we have I2 going from the top right to the bottom left, and I3 goes in the opposite direction. So again, we use with a negative sign. So we have I2 minus I3 equals 0. Now let's just do the same for R3. For mesh 3. So I start from this point again. We go through R8. So the net current in the direction of I3 through R8 is going to be I3 minus I2. Then we get to R3, which is common between mesh 3 and mesh 4. So the net current that goes through R3 in the direction of I3 is going to be I3 minus I4. And then finally we have R4, which is not common between two meshes, and only I3 goes through it. So we have R4 multiplied by R3 equals 0. And finally, for mesh 4, we have, let's say, if we start from here, we have R3 common between mesh 4, mesh 3. So we have R3. The net current in the direction of I4 is I4 minus I3. Then we get to R2. The net current in the direction of I4 is I4 minus I2. And finally, we have R7, which only has I4. So we have R7 multiplied by I4 equals 0. So these are the 4 equations that we can write for this circuit, and they are completely independent. So if we know the value for the voltage source and the values for the resistors, we can find the values for the mesh currents. Of course, let's say you found the values for mesh currents, I1, I2, I3, and I4. Now you want to find the value for the current that goes through R6. So the relationship for that is very simple. So if you say the current of I of R6 is in this direction, so I of R6 is going to be equal to I1 minus I2. You can do the same for the rest of them as well. So mesh current method, also node voltage method, are powerful techniques that help us reduce the number of unnecessary equations that we need to solve in order to have a fully solved circuit. So doing this simple algebraic equation is not something that needs to be done simultaneously with other equations, right? It can be done after the fact. So that's why we can call this an unnecessary equation. You find I1 through I4, and then whatever variable that you have in your circuit can be easily calculated using basic algebra from these known variables. So if I want to write this, let's say, in a matrix form, what I can do is I basically collect all the coefficients for these currents. So for the first one, we have R1 plus R5 plus R6. For I2, we have negative R6. And for I3 and I4, we have 0. So this is for this equation. So we have I1, I2, I3, and I4, which equals, it's Vs for the first row. For the second row, it's going to be negative R6, positive R2 plus R6 plus R8. For I3 is going to be negative R8, and for I4 is going to be negative R2. For the third row, the coefficient for I1 is 0. The coefficient for I2 is going to be negative R8. The coefficient for I3 is going to be R3 plus R4 plus R8. And for I4 is going to be negative R3. And finally, for the last row, we have 0 for I1, we have 0 for I2. For I2 we have negative R2. For R3 we have negative R3, as we have here, R3. And for I4 we have, let me just write it like this, we have R3 plus R2 plus R7. And the other side for these three equations is 0. So this is AX equals Y. So if you want to solve it as a linear equation in the form of AX equals Y, these are going to be the coefficients for these linear equations. So we saw those basic examples. Now what happens if there are dependent sources in the circuit? So the answer to that is that we use the same analogy as before, but we supplement those equations by the constraints that are imposed by the dependent sources. So let's just take a look at this circuit. So this one has 3 meshes. So we consider this one mesh 1 with current I1, this one is I2, and this one I considered I3. So when you look at this circuit, you see that if we went with node voltage method, it was much easier, right? Because for the node voltage method, here we had this independent source that are connected to this essential node. If we consider this to be the reference node, that means that the voltage at this node is already there. So we only need to figure out the voltage in this node and this one, right? But for the purpose of this video, I want to use the mesh current method. So let's just write the KVL for each one of these individual meshes. For this one, we have negative 50 plus 5 multiplied by, what is the net current in the direction of I1? Is going to be I1 minus I3. So we have I1 minus I3. What is the net current for the 20 ohm in the direction of I1? It's going to be 20 multiplied by I1 minus I2. That equals 0. Let's just do the same for the second mesh. So this one was for the first mesh, this one for the second mesh. We have 20 multiplied by I2 minus I1 plus 4 multiplied by I2 minus I3 plus 15 I5, which equals 0. Again, following the passive sign convention. And the third one is, if I start from this point, we have 5 multiplied by I3 minus I1 plus 1 multiplied by I3 plus 4 multiplied by I3 minus I2, which equals 0. So you see we have 3 meshes, which means we have 3 mesh currents. We have 3 equations, right? But in this equation, we have this I phi. So how can we find the value for I phi, or at least the relationship for I phi? If you look closely, you see the I phi is defined as the current that goes from top to bottom in this 20 ohm resistor. So I phi is basically I1 minus I2. So if we replace I phi in this equation, then we have 3 simultaneous equations that can give us the values for the 3 mesh currents. So let me just quickly write that down. So the first one is going to be simplified to 5 I1 plus 20 I1 is going to be 25 I1 minus 20 I2 minus 5 I3 equals 50. The last one, if I want to write it, is going to be negative 5 I1 negative 4 I2 4 I2 and then 5 6 10 I3 plus 10 I3 equals 0. And finally, for this equation, if I write it like this, we have 20 I2 minus I1 plus 4 I2 minus I3 plus 15 I1 minus I2, which equals negative 20 I1 plus 15 I1. It's going to be negative 5 I1. Positive 20 I2 plus 4 I2, it's going to be 24 I2. Negative 15 I2, it's going to be 9 I2. 9 I2. And then finally negative 4 I4. So negative 4 I4 equals 0. So if I write it in the matrix form, we have 25, negative 20, negative 5, this one is I1, I2, I3, and it is equal to 50. The second one is negative 5, 9, negative 4, and this is 0, and this one is for I3. Yeah. And then finally we have negative 5, negative 4, and then 10 I3 equals 0. So solving this 3 by 3 system of linear equations would give us the value for I1, I2, and I3. So one thing that you should consider is that writing this system, even though it is an important step, but it is not the final solution. So to keep these videos short, I don't go through the solution of these equations. And I would assume that you use calculators to find the solutions anyway, right? But just know that when you get to this, the solution is, you can say, practically there. So in this video, you got introduced into the mesh current method. We saw how we can find the meshes in a circuit, how we can define the mesh current that can help us reduce the number of equations in comparison to the systematic approach. And then we saw several examples of applying the mesh current method.